Hello and welcome to this screencast on differentiation. So, first things I'm going to do is I'm going to draw a set of axes and label my horizontal axis x and my vertical axis y. And on this set of axes, I'm just going to draw a function and I'm going to call this function y equals f of x. Okay, so the purpose of differentiation is to be able to find out what the gradient of this function f of x at a particular point. Okay, so let's say that's my point. So the value there is going to be x, okay, and so therefore the value of the y-axis is going to be f of x. Okay, so what is the gradient of the line at that point? So if I was to draw a straight line, okay, that goes through the point, I want to know what the gradient is of that red line there. Okay, right, so the gradient, m, is equal to the change, which is represented by the Greek letter delta, in the y direction divided by the change in the x direction. So what I need is I need a value for my delta y and I need a value for my delta x. Okay, and to find that value, what we do is we have another point somewhere along my function, and let's say that's the point x plus h. So that's going to be x plus h. Okay, and the value at the y-axis is going to be f of x plus h. Okay, so now I have my delta y, which is the vertical distance, and I have my delta x, which is the horizontal distance. Okay, so what I can do is I can approximate delta y by saying that's f of x plus h minus f of x, so that's a change in the vertical direction, divided by h, which is then the change in the horizontal direction. Okay, so that's one way of approximating the gradient. But if I draw the line, the straight line between, just pretend that's a straight line. If I draw the straight line between those 2 points, you can see the gradient of the blue line is nowhere near the gradient of the red line, so it's not a very good approximation. Now, in order to improve the approximation, what I could do is I could move this blue point closer and closer to my original value of x. Okay, just close enough so that it's barely conceivable how far apart x and x plus h are. And what we're going to do here is we're going to use what's called a limit. Okay, so what I'm going to say is I'm going to say that the dy over dx. Now, you might ask what this is. This is actually another way of writing delta y over delta x. So instead of delta, we're using d. Okay, so this, remember, this is just simply a gradient. So dy over dx. What I'm going to say is, let's pretend that h is very, very, very small. So I'm going to say limit, what is the limit of this value, the approximation of the gradient, when the difference between x and x plus h is very, very small. Okay, so what we have here is f of x plus h minus f of x, all divided by h. Okay, so that'll give us the gradient of our function f of x at the point x. And this is the basic definition of a derivative. Okay, so let's have a look at an example. Okay, so let's say I have a function, simplest function, or one of the simplest functions, y equals x squared. Okay, so therefore dy dx would be equal to the limit as h tends to 0 of f of x plus h, so that will be x plus h squared, minus x squared all over h. Okay, so I just explained this numerator. So we have the value of f of x plus h, so whatever the input is, the output is squaring the input. Okay. What we can do now is just expand out the bracket on the numerator. Okay, so we have the limit, we have x squared plus, excuse me, plus 2h times x plus h squared minus x squared. So all I've done there is I've expanded out the bracket on the top. Okay, well, now I've expanded that bracket, I could clean this up a bit. So I've got an x squared and a minus x squared. So I'm going to get rid of those two. And I'm also going to divide throughout by h. And what we're left over with is 2x plus h. Okay. Now, this limit, as x tends to 0, this h here, excuse me, this h term again is going to be basically 0, it's going to disappear. So what we have is the derivative of y equals x squared is simply 2x. Okay, well that's for a specific function. What about for a general function of the form y equals x to the power n? Okay, so what I'm going to do now is show you the derivative, or the derivation of the derivative of y equals x to the power n. Okay, so again, following from first principles, we have the limit as h tends to 0. Okay, and f of x plus h will be to the x plus h to the power n minus x to the power n, all divided by h. Okay, so using the binomial theorem, and if you're unsure about that, I suggest you have a look at the screencast on the binomial theorem. The expansion is x to the power n plus n choose 1, x to the power n minus 1 times h plus n choose 2, x to the power n minus 2 times h, and that's going to go on lots and lots of times for n times. You're going to end up with n choose n, h to the power n, and finally the minus x to the power n at the end. Okay, so all of these terms here is the binomial theorem expansion of that bracket there. Okay, and not forgetting this is all divided by h. Okay, so let's do some tidying up. So we have the limit as h tends to 0, x to the power n minus x to the power n disappears. So we end up with n choose 1, x to the power n minus 1, and h divided by h is simply 1, plus n choose 2, x to the power n minus 2 times h, plus a load of other terms which also include h. So every term after this one here has an h is multiplied by h. Now since the limit is as h tends to 0, all of those terms are going to disappear, and we're left with this lone term here. Okay, so if I just, here we have the binomial coefficient n choose 1. Just see what this is equal to. So from the definition of the binomial coefficient, we have n factorial divided by 1 factorial times n minus 1 factorial. So if I expand out top and bottom, I have n times n minus 1 times n minus 2 all the way down to 1. And on the bottom, I have 1 factorial, which is simply 1. That's divided by n minus 1 factorial all the way down to 1. And as you can probably notice, lots of cancelling out leaves us with just n. So therefore, what I can say is for the function y equals x to the power n, the derivative dy dx is equal to n times x to the power n minus 1. So for example, if I had y equals x to the power 3, dy dx, or the derivative, is simply 3x squared. Okay, and that's differentiation.